Welcome to this explainer. Okay, today we're cracking open the core dilemma of the internet. Whenever you type in a web address, your data zips across the globe, bouncing through dozens of completely unknown networks. Now, we all know encryption keeps that data hidden from prying eyes, right? But here's the real question. How do you know you're actually securely talking to the right server in the first place? Let's meet the web's invisible bouncers.
Seriously, think about it. When you connect to a server that claims to be Google, it hands your browser a public encryption key. Your browser is smart. It can use signature verification to ensure the server actually holds the matching secret key. Boom, you've got a secure encrypted channel. But how does your computer know that specific public key actually belongs to Google? What if it belongs to some clever imposter sitting a few tables away in your coffee shop? This right here is what we call the authentication problem.
So, Section 1, the authentication problem.
To really understand how we solve this today, we kind of have to look back at the earliest way we tried to fix this digital identity crisis. It was a scheme called Trust on First Use, or TOFU for short, and it's exactly what it sounds like, incredibly straightforward. Instead of relying on a whole complex system of third parties, your client just maintains a local table. The very first time you connect to a server, your computer basically says, well, all right, I guess this is your public key, and saves it. If you've ever used SSH or fetched code from GitHub, your machine is using TOFU. It memorizes the key the first time and just expects to see that exact same key every time you return.
TOFU is beautifully simple. You don't need any extra trusted parties involved. If you get the right key the first time, you are secure. But here's the crucial point. What if a network attacker intercepts that very first connection? Well, you'll unknowingly trust the wrong key forever, or at least until you realize something's broken and manually fix it.
Moving on to Section 2, trusting the authorities.
Because of that fatal flaw in TOFU, the web desperately needed a more robust standard solution. We needed the equivalent of passport agencies, or, nightclub bouncers for the internet. Enter the Certificate Authority, or CA. A CA is a trusted third-party organization that maintains a massive table linking domain names, like might.edu, to their correct, verified public keys. When a server wants to prove its identity to your browser, it doesn't just send its public key anymore. It sends a certificate. Think of this as an ID card, a message signed by the CA's secret key confirming the server's identity ahead of time. Your browser then uses the CA's widely known public key to verify that signature.
But wait, how does your browser know the CA's public key in the first place? Well, the answer is roughly 100. When you download a browser, like Google Chrome, it comes with about 100 trusted CA root keys permanently baked right into the source code. The developers at Chrome, Apple, Microsoft, they all curate and maintain these lists of fully trusted authorities.
Which brings us to Section 3, blind spots and exploits.
Now, CAs seem like a great airtight system, right? But what happens when attackers figure out the system's blind spots? Now, what's really interesting about this is how specialized the protection is. Certificates brilliantly stop cryptographic tampering. If an attacker tries to swap in their own public key, the certificate signature flat out fails. If they manage to get a valid certificate for their own site, well, the name won't match the site you requested. But look at where they fail completely. They are totally useless against simple visual phishing. If an attacker registers Amazon.com but replaces the letter O with a 0, the CA is going to issue a perfectly valid certificate for that literal exact name. To the underlying math, everything is perfect. To the human user, it's a trap.
And this brings up a massive vulnerability known as the name binding flaw. Certificates only work when the user's intent perfectly matches the literal name the CA signed. Take MIT's secure Wi-Fi, for example. When your laptop connects to that Wi-Fi, it does a secure handshake with a background login server. But that server has this complex, obscure name, something like w92-radius-wireless1.mit.edu. Actually, scratch that. As a user, you never saw that. You just clicked a button that said MIT Secure. Because your intent doesn't match the hidden server name, your device has no choice but to fall back to the vulnerable TOFU model. If an attacker spoofs the Wi-Fi, your device might just hand over your username and password without you ever realizing the certificate name was completely different from what you intended.
So the industry obviously tried to fix these trust issues. For a while, we had this grand experiment with extended validation certificates. Instead of just quickly checking if you controlled a domain, CAs charged a ton of money to check your actual physical organization. They would literally call places like the MIT Federal Credit Union, ask them to send over faxes with official letterheads, and manually verify physical addresses. In return, browsers gave these websites a massive green bubble in the URL bar. But the experiment totally failed.
Users didn't know when to expect a green bubble versus a normal secure connection, and ultimately they just didn't care. The web eventually decided that domain validation, just proving you mathematically control the web address, was the only practical path forward.
Section 4. Proving who you are.
So, if we aren't using faxes and phone calls anymore, how do modern CAs actually verify that you own a domain today? Well, it's all automated now using protocols like ACME, championed by organizations like Let's Encrypt. Think of it like a cryptographic scavenger hunt on port 80. Your server asks the CA for a certificate. The CA says, okay, prove you own this domain. Take this random secret number, a nonce, and post it on a specific hidden page on your website. The CA then just sends a regular internet request to that page. If it finds the random number sitting there, boom, it proves your server controls the domain and the CA issues the certificate.
But you're probably thinking, a clever attacker could just try to intercept that single verification request, right? To stop this, Let's Encrypt uses the absolutely brilliant escalation called multi-perspective validation. Instead of checking the challenge from just one server, the CA checks it from 5 different points across the globe simultaneously. To fake this, an attacker couldn't just sit on a local network. They would literally have to compromise massive DNS servers or multiple global internet service providers all at the exact same time.
All right, Section 5, watching the watchers.
Okay, let's dive into this. What if the CA itself gets hacked or tricked? What if a trusted authority goes rogue and starts issuing fake certificates for your website? This is where the Certificate Transparency, or CT log, comes in. It's basically a public, append-only database operated completely independently from the CAs. Before a CA gives a certificate to a server, it absolutely must send it to the CT log and get a cryptographic receipt. Modern browsers like Chrome are strict about this. They will flat out reject a perfectly valid certificate if it doesn't carry this receipt proving it was publicly recorded.
I love this quote because it really captures the magic of the CT log. Even if a client does get tricked with a bad cert, at least someone out there knows. Because these databases are fully public, anyone can go browse these logs right now. You can audit your own footprint and catch misissued certificates in plain sight. If a CA makes a mistake or gets tricked, the evidence is permanently logged for the whole world to see, and browser developers can immediately take action to remove that CA from their trusted list.
And finally, Section 6, pulling the plug.
This brings us to our final, messiest problem, handling stolen keys or sold domains where old certificates are still active. Like, what happens if your private key is stolen? Or say a domain like fb.com gets sold to Facebook, but the previous owner still holds an active, unexpired certificate. The security community has literally run in circles for years trying to figure out how to pull the plug on bad certificates. First, they tried long expiration dates, but waiting years for a compromised cert to expire was way too risky. Next came certificate revocation lists, or CRLs, but downloading massive lists of every revoked certificate on the internet was too slow and the data was always stale anyway. Then they tried OSCP, a protocol to check a certificate's status in real time. But that added huge latency to every connection and completely destroyed user privacy because suddenly the CA knew every single website you were visiting. Finally, they tried OSCP stapling, where the server fetches its own real-time proof of validity and hands it to the browser.
And this brilliantly illustrates the final twist. After decades of struggling with incredibly complex revocation protocols, the web realized that the ultimate solution is just issuing super short-lived certificates. Thanks to automated systems like Let's Encrypt, instead of issuing certificates that last for years, they're issuing them for 90 days, and soon, maybe just 7 days. If a certificate expires in a week, you don't really need a complex system to revoke it. You just wait a few days, and the problem literally solves itself.
The invisible bouncers of the web are constantly evolving, right? We're trading faxes for automation and long-term blind trust for constant short-term verification. Which leaves me with a question for you. If anyone can see the digital receipts of the internet, have you checked the transparency logs for your own website recently? It might be time to look up your own digital footprint. Thanks for joining us for this explainer, and keep questioning the systems that keep you safe.